All right, so now we're to the fourth section of chapter 5, and it is called the fundamental theorem of calculus. So, it only took us 4 chapters and 4 sections to get to the fundamental, the basic theorem of calculus. All right, the fundamental theorem of calculus is expressed in 2 parts, and this is the first part. It says if f is continuous on the closed interval from a to b, then the function capital F of x is equal to the integral from a to x of f of t dt, and it has a derivative at every point in the closed interval from a to b, and so d capital F dx is equal to the derivative of, with respect to x, of this integral that we just talked about, the integral from a to x of f of t dt, and that equals f of x, little f of x. So essentially what this is telling us is that derivatives and antiderivatives are essentially inverses of one another to a certain extent. So that's what this is actually telling us. Remember, anytime we see a capital F, we're thinking about that as an antiderivative. So capital F is the antiderivative of little f of x, or little f. Now, there are a couple of rules here. The first fundamental theorem, there's some rules that have to hold in place. And the first one is you have to have the derivative of an integral. If you have the derivative of an integral, then the next thing you want to do is you want to make sure that the derivative that you're taking with respect to matches the upper limit of integration. And then the third part, the lower limit of integration must be a constant. If it fits those 3 requirements, then notice all that we're doing. We're taking this x right here, and we're plugging it in place of that t right there, and that's our new expression. So essentially just changing variables. All right, so for instance here, we have the derivative with respect to x of the integral from negative pi to x of cosine t dt. So as we're looking at this, go through our steps here. It's the derivative of an integral, yes. The derivative that we're taking with respect to matches the upper limit or the variable there. Yes, that one works. And the lower limit of integration is a constant. It is. Now, we could do this the long way, but we already know that this is going to fit. But I want to show you the long way just so you can see where this comes from. If we were to take the antiderivative of cosine t, we know we're going to get sine t. And remember, we're still taking the derivative of this. But I'm evaluating this from negative pi to x. Now, if I do just the brackets here, I've got d dx of sine x minus sine of negative pi. Now, when I take the derivative of this, what's going to happen when I take the derivative of sine x? Well, I'm going to get cosine x. What's going to happen when I take the derivative with respect to x of negative sine negative pi? Well, sine of negative pi is going to be a number. It's actually going to be a 0, but even if it wasn't a 0, the derivative of that 0 would be 0, so we're going to end up with just cosine x. Now, go back and look. We went through our checklist. The derivative with respect to x of x, so we're taking the derivative of an integral, the derivative with respect to and the upper bound match, and the lower limit of integration is a constant. So our fundamental theorem tells us that all we're going to do is we're going to take that x right there, we're going to put it in place of that t right there, and we get cosine x, which is the exact same thing we got from doing it the long way. All right, so let's do this one just the shortcut way. So first things first, does it fit our limit, or does it fit our rules? Is it the derivative of an integral? Well, d dx of the integral, yep, sure is. Does the derivative match the upper limit of integration? Yep, sure does. And is the lower limit of integration a constant? 0 is a constant, so what do we know? We know all we're going to do is we're going to take that x right there and replace it everywhere we have a t in this one. We get 1 over 1 plus x squared. That is the first part of the fundamental theorem. It's just that easy. All right, now this one's a little different. Here, we actually have to do this, and I'm going to show you the long way first. And then I'm going to get you to kind of figure it out what the deal is. So once again, if we take the antiderivative of cosine t, we got d dx of sine t evaluated from 0 to x squared. And then when we find that, when we evaluate that antiderivative here, we're going to plug in x squared, so we're going to get sine of x squared minus sine of 0. Now sine of 0, of course, is still going to be just some random number. It actually is 0 there. But in this case, if it had been sine pi, it would have been the same thing, or pi over 2. That 1 would still cancel out when we take the derivative anyway. Now when you take the derivative of sine x squared, what are you going to get? Well, you're going to get cosine x squared times 2x. And then what happens when you take the derivative of the negative sine of 0? That's going to go away and give you 0. So you end up with 2x cosine x squared. All right, now, so let's see how we can adjust just a little bit the fundamental theorem to get what we want here. So we've got the derivative of an integral, yes. The derivative matches the upper limit of integration. No, it doesn't in this case, but it is a variable of that. So this is the variable that we have up here. That is enough. Check. And then the second part, the lower limit has to be a constant. So check. So we're going to adjust it just a little bit and say, as long as the variable that we're taking the derivative with respect to matches the derivative or the variable in the function up the upper bound, we're okay. And then all we're going to do is we're going to plug in this there the same way we did before. And what do we multiply by over here? What is that? That is just the derivative of this right here. And where does that come from? Well, that comes from the chain rule. So we get 2x cosine x squared. Now, once again, remember when we talked about the chain rule, we said if you always treat every single problem like a chain rule problem, you never forget the chain rule. So with that one we just did just a second ago over here, we plug the x in. If we multiply by the derivative of x, we get 1, so we still are going to get this thing correct. So always remember when you do the fundamental theorem, when you do the plug-in part, always multiply by the derivative of what that variable thing is. So we get 2x cosine x squared. Just remember to use the chain rule when we do these. All right, now you guys try this one. There's a little trick to it. What do we know about the upper and lower bounds here? Well, the upper and lower bounds are in the wrong place. Upper bound is not the variable that matches this, and the lower bound is not a constant. So we can actually change this by throwing a negative out front. So think about this as negative d dx of the integral from 5 to x of 3t sine t dt. So in this case, that negative right there, and we've got that rule that says if we throw a negative out front, we can flip our upper and lower bounds there. All right, so at that point, we check, Do we have the derivative of the integral? Yes, we do. Does the derivative match the upper limit of integration? Yes, it does in variable form. And then, is the lower limit of integration a constant? Yes, it is. So in that case, this is going to fit the fundamental theorem now, but don't forget this minus out here. So we've got negative, and then we're just going to plug that x in everywhere we have a t inside. So 3x sine x. And that is our answer using the fundamental theorem. All right, now what about one like this? One here where we've got a situation where we are taking the derivative of an integral, so that one checks off. The derivative does match the variable we've got in the upper bound, but the lower bound is not a constant. Well, we can actually get around this, and we can get around this by imagining some constant that is in between 2x and x squared. And guys, it doesn't have to really be in between it. But we can imagine as if one was, and it makes it a little easier for us to figure this thing out. So we can actually do this as the derivative with respect to x of the integral from 0 to x squared of 1 over 2 plus e to the t dt plus the integral from 2x to 0 of 1 over 2 plus e to the t dt. And you can write these in any order you want to, it doesn't matter. But the thing is, now when we distribute and take the derivative of each individual part here, we're going to have ddx of this thing, 0 to x squared of 1 over 2 plus e to the t dt plus, now right here we can notice that our bounds are not the same. We're still taking the derivative of that, but I'm going to go ahead and throw a negative out in front of that. So minus ddx of the integral from, if I put a negative out front, I can flip my bounds, and I'm going to go from 0 to 2x of 1 over 2 plus e to the t dt. All right, so now at this point we can treat each one of these separately. So do I have the derivative of a integral? Yes. Does the derivative match the variable of the upper bound? Yes, it does. Is the lower bound a constant? Yes. So what does that mean? Well, that means I'm going to take this thing right here and I'm going to plug it in everywhere I got a t. So this first part is going to become 1 over 2 plus e to the x squared. And then don't forget, you're going to multiply by the derivative of that thing you plugged in, 2x. All right, and then minus, same thing over here, derivative with respect to x of the integral. So derivative of the integral, our derivative matches the variable in the upper bound, and lower bound is a constant. So we're good there. It means we're just going to plug in the 2x. So we end up with 1 over 2 plus e to the 2x, and then multiply by the derivative of what you plugged in, times 2. All right, so we end up with 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. So you can split this up, because remember, what are we really doing here? We're really going from 2x to x squared, and we're saying that there's a 0 in here somewhere. So I'm going from 2x to 0, that's this one over here, and then I'm going from 0 to x squared. And guys, you could have just as easily put 10 in here. It doesn't matter as long as it's a constant. We could put 10 in between there. What happens when we take the derivative? The constant goes away. You can call that thing anything you want to. You could have called it 10 million. That's not even close to 10 million, is it? There we go. And here's the thing. It doesn't actually, whatever number you choose doesn't actually have to be in between here. Watch this. Let's say we choose a value that is outside of it. Let's go ahead and choose a value over here and say that that's 0. Well, I go from 2x to 0, and then I go from 0 to x squared. So this is negative because I went backwards, and this is positive. So what do we actually end up with anyway? Only the stuff between 2x and x squared anyway. So we only get what we're looking for as it is. All right, now part 2 of the fundamental theorem of calculus says if f is continuous at every point on the closed interval from a to b, and if capital F, or the antiderivative of f, is any antiderivative of f on the interval from a to b, then the antiderivative, or the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. Now, this we've already looked at. We have already saw this in the last section when we figured out how to evaluate this definite integral right here. Definite integral is an integral where you have an upper and lower bounds. Indefinite, which we'll talk about later, you don't have upper and lower bounds and you can't actually come up with a number. You're just looking for the antiderivative. But anyway, so if we take the definite integral here, we're going to take the antiderivative of this function here. We're going to plug in the upper bound, and we're going to subtract when we plug in the lower bound. That's what you do. So antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. This is also called the integral evaluation theorem because, well, guess what? That's the theorem that tells you how to evaluate an integral. All right, if f is continuous on an open interval I containing a, then f, defined by f of x equals the integral from a to x of f of t dt, is continuous on I. Justify your answer. All right, if f is continuous and we're looking for what? F of x being continuous, which is defined as the integral. Well, remember the integral is just finding what? The area under the curve. And if the curve is continuous, then the area will be a continuous value as well. Also, we know that if we've got this thing, the fundamental theorem of calculus guarantees that f is differentiable on I, so it must be continuous on I as well. So true. All right, if b is greater than a, then the derivative with respect to x of the integral from a to b of e to the x squared dx is positive. Justify your answer. Well, here's the thing. Remember what e to the anything looks like. It is an exponential function like so, and it's all above the x-axis. And if b is greater than a, and we're going from a to b, we're going from here to there, or something along those lines. What do we know when we find the area under the curve there? Well, that's going to be some number, right? So this part right here is going to give us some number. What happens then when we take the derivative of that thing? If we take the derivative of some number, well, that's a constant. The area from a to b under the curve from a to b is going to be a number. It's going to be constant. It's not changing. So then when we take the derivative of that, it's going to be 0. So this is false. Now, if we had gotten rid of this part, oh, hold on. If we didn't have that part, what will we know? Then that integral is going to be positive. But because of the derivative, this part right here finds us a value This part finds us a value, the integral finds us a value, a number. So this is a big number. We take the derivative of that number, and it's going to go to 0. All right, let f of x be the integral from a to x of the natural log of 2 plus sine t dt. If f of 3 equals 4, then f of 5 equals what? All right, so this is an accumulation. It's going to keep adding values to it. So f of 5, we're going from some number, we don't know what it is, up to x. Well, here's what we're doing. If we know that f of 3, let me get this smaller here, thought I'd already done that. If f of 3 equals 4, that means if we start our integral at 3, we know we have 4 and then plus whatever we're going to accumulate from 3 to 5. So f of 5 is going to equal 4 plus the integral from 3 to 5 of the natural log of 2 plus sine t dt. Now, once we get that, we can actually find that using a calculator. This one would be a calculator problem. So let's go ahead and pull a calculator up. Let me clear all that. And we're going to do 4 from here plus, and then alpha window. I'm doing integration here, so 4. Then all I'm doing is plugging in my values. 3 to 5 of the natural log of 2 plus sine x. And then close the parentheses. Whoop, wrong. All right, and then plug in x for there and hit enter. And it gets me 4.555. So answer choice D. So when x is 3, we have a value of 4 already. And then this thing is just adding up how much accumulation is going on from 3 to 5 that we're going to add to the value of 4. So the function value at 3 has a value of 4. This tells you how much the function is adding as you go from 3 to 5. Don't make this more complicated than it is. It's actually really easy. Just remember that when we have a point here, then we know that that's where our function is going to start. This is our value, and that's where it's going to start, and we're going to integrate to add to that from there. All right, what is the limit as h approaches 0 of 1 over h times the integral of x from x to x plus h of f of t dt? All right, now this thing looks way more complicated than it actually is. Let's look at it, and I'm going to break it down for you here. If we evaluate this part right here for right now, what's going to happen? We're going to take the antiderivative of f of t, which is going to be capital F of t, and we're going to plug in the upper bound minus the lower bound. So we're going to have f of x plus h minus capital F of x, and then the 1 over h right here, that's just dividing by h, right? And then we're taking the limit as h approaches 0. So hopefully you can recognize this. This is the definition of the derivative. So when we take this thing, we're taking the derivative of f of x. Well, what's the derivative of capital F of x? Well, it's little f of x. And that's where our answer comes from. All right, at x equals pi, the linearization of f of x equals integral from pi to x of cosine cubed t dt is what? So we want to find the linearization, otherwise known as the tangent line of this thing. So f of x, when x is pi, well, what is f of pi? Let's go ahead and break it down. Remember, we've got y minus y1 equals m times x minus x1. So when we put this in calculus mode, this is y minus f of pi equals f prime of pi times x minus pi. So I've already plugged in one piece of information. I've got to find another. So what is f of pi? Well, that means I'm going to plug in, I've got f of pi, which means everywhere I've got an x, I'm going to put in a pi. So I'm doing the integral from pi to pi of cosine cubed t dt. Now, here's the thing. If we're finding the area under the curve, we're going from pi to pi, there is no width to it, so that means that this has to equal 0. So that means we have y minus 0 right here. And then we have to find the derivative of that thing evaluated at pi. So let's break this down. We've got f prime of x is going to equal the d dx of the integral from pi to x of cosine cubed t dt. You guys see where we're coming from there? We're taking the derivative of this. We have to take the derivative of both sides. Derivative of f of x will be f prime of x. And we've got to take the derivative of this, which gives us a prime candidate for the fundamental theorem of calculus here. Part 2. So if we take the derivative of an integral, yes. Lower or derivative matches the upper bound of integration variable, yes. And the lower bound is a constant, yes. So that means all we have to do is plug in an x right there. So f prime of x is going to equal cosine cubed of pi. Well, cosine cubed pi, nope, sorry, that's wrong. That's cosine cubed of x. So now when I find f prime of pi, that's where I get cosine cubed pi. And cosine pi is negative 1. Negative 1 to the third power is going to be negative 1. So that means my slope is negative 1. So when I put all this together, I'm going to end up with y is equal to negative 1 times x minus pi. Now you can go ahead and distribute that, and you could get y is equal to negative x plus pi, or pi minus x. All right, the area of the region enclosed between the graph of y equals the square root of 1 minus x to the fourth and the x-axis is what? All right, so we're going to use a calculator again. Let's go ahead and pull our wabbit up. And we're integrating this thing, but we're going to have to actually find what part we're using. So between the graph and the x-axis, I don't want that over there, I want it over here. So we're going to have to graph this. So let's go ahead and go to y equals, and we're going to put in the square root of 1 minus x to the fourth. All right, and then we're going to graph it. And my graph here, notice it looks absolutely nothing like I need to. So let's go ahead and go to the zoom. And I want to do a zoom decimal, so 4. That'll give me a better idea of what I'm looking at here. So that's what I'm looking at right there. So I want to find the area of the region enclosed, which means I'm going to, let me go ahead and zoom in a little bit here. We'll do number 1, a Z box. All right, now don't be mistaken, this is not a circle because of the x to the fourth. If it was at minus x squared, then it would be a semicircle, and this is not a semicircle because of the x to the fourth, and it's, you know, you can see it's pretty obvious. So how do we find the area under this? Well, there's a couple of ways you can do it. Right here with this, you can actually go in here and calculate and find number 7, f of x dx. This is not the best way to do this. I'm just going to go ahead and tell you. And you're going to go from -1 to +1. And it will actually go in here and shade this in and show you what the value is. The value is 1.748093. So our answer choice is E. Now, the biggest reason that you would actually want to use this, let me go ahead and, wrong. All right, so this is going to clear the shading, so it's not going to be there anymore. And I can look at the graph again. So I know I'm going from -1 to +1. The best way to do it is still with this thing, with 4, because that actually does the numerical integration. The graph can give you wrong answers. Not wrong grammatically, but it can be off that third decimal place because it's not quite as accurate as it needs to be. So we're going from -1 to +1. This one worked out okay. I'll just go ahead and tell you. But there are instances where you're going to get mistakes there by that third decimal place. Graphing or calculating on the graph is not accurate enough. So we end up with the second of 1 minus x to the fourth. And then integrating with respect to x. All right, so 1.7480383939. So that's the answer that we should come up with. So E. All right, that's all section 4. These are going pretty quick, aren't they?